Hello, hello. Let me know if you can hear me. I set the stream on low latency mode based on other people's recommendations. So let me know if there are any buffering issues as well. Also, just so you know, for other changes, I'm going to try and put the chat on screen. This will allow me to edit videos after the fact. I can probably cut out some of the pauses. And hello, Ken. And hello, Brian. Thank you for being here. So my idea was I would just take the chat and put it on screen. And that way I can edit the video. So every time you edit the video in YouTube, it gets rid of the chat on the side. So I figured if chat was permanently embedded on screen, I would be able to edit the video after the fact and get rid of some of the pauses, because I know some of you have been complaining about that. Anyways, let's get started. So today I wanted to derive E equals mc squared from scratch, truly from scratch. This is something that took a little bit of research on my part, because of course there are a lot of derivations all over the place that are very much not from scratch. But I did find this lovely, lovely paper by Terence Tao, where he derives E equals mc squared on the level of math that basically a high school student would have. If you'd like to read this on your own, you just type in Terence Tao special relativity into Google, and it'll probably be like the first or second result. So this is the derivation that we are going to follow, and it's like a 13-page thing. Though I'm going to this is already a very concise derivation. I'm going to make it even more even more concise, basically. So let's get started. So to warm up, one thing that you perhaps need to do this track of this derivation is you need to understand space-time diagrams reasonably well. So space-time diagrams it's a pretty simple concept. You know, you have time on the y-axis and a position on the x-axis. We're going to assume the universe is one-dimensional. The math doesn't change at all. You know, if you have 3 spatial dimensions, you could have 7 spatial dimensions. I don't think the math would change at all. So just to make life a little bit easier and to avoid messiness, we're just going to consider the position of things on one axis, and this is time. So for example, the quote world line of an object that stays perfectly still. So if you stay perfectly still, let's say you start at this position, and you do not move ever, you know, as time changes, then your quote world line, or the line that describes your position as time changes, would just be a straight vertical line. Hopefully that seems perfectly reasonable. Or for example, maybe you start at this position and you move at some velocity, some positive velocity, so your position changes with respect to time, then your world line would look something like this. Okay? And so, for example, you can use these types of diagrams to solve questions like, you know, when, so if you have two people, one starts at this position and the other person starts at this position, at what time will they meet? You can just look at essentially where the lines intersect one another. Hopefully that makes reasonable sense. So it's just a way to kind of graphically represent problems involving position and time. The only thing that I find counterintuitive about this is that the way physicists do it, time is on the y-axis and position is on the x-axis, whereas the way I'm used to doing things, my background is mathematics, by the way. I'm I'm definitely by no stretch of the imagination a physicist, but I've been trying to learn more and more physics lately, and so this is a peek into my attempts to learn more physics. But hopefully this diagram makes sense. And as I was saying, I'm used to putting time on the bottom axis and position on the vertical axis. So you might see me lapse occasionally and do that. Hopefully you don't mind if I do that. Just so you know, if you were in a physics class and you were drawing these space-time diagrams, the time would be the y-axis and your position would be the x-axis. So you can imagine as you change over time, time moves kind of in this upward direction. Hopefully that makes sense. Hopefully I'm not like blowing your mind over here. So as a warm-up, and to convince you that these space-time diagrams are indeed useful, I have a little warm-up puzzle for you guys. I hope you're excited. And this warm-up puzzle is in the paper too. I'll give you another version of it that's also not in the paper as a homework exercise if you're interested. So here is my puzzle for you. Okay, you are at an airport. Okay, you're at an airport. And this airport has a moving walkway. I mean, I assume you've seen these before. They're these really long treadmills, and you stand on it, right? You stand on the moving walkway, and it just does the the moving for you. So just to assume like simple numbers, let's say you walk at 1 meter per second. This is like a reasonable speed, good units. Let's say the walking treadmill also goes at 1 meters per second. So for example, if you're walking on the walking treadmill, you would then be traveling at 2 meters per second. Okay, so you get a little speed boost because you're walking on the walking treadmill, and in addition to that, you're walking yourself. So you would be going at 2 meters per second if you were going on the walking treadmill. Okay, now beyond that, there's an issue. Your shoelaces are untied. Okay. So you have to pause at some point between where you are and your terminal. Okay, so imagine you are someplace. Your airport terminal, which is where you are going, is out there somewhere. Okay, and you have to pause at some point to tie your shoes. And so for a brief interval of time, you will not be moving, right? So the question is, or at least the question I have for you guys is, do you think you want to tie your shoes on the moving walkway, on the moving treadmill, or not? That is the question I'd like to start with. Okay, so pretty simple question. You're walking, and you can choose to pause and become completely stationary and tie your shoes, or you can get on the moving walkway and then tie your shoes. And your goal is to get to your terminal as quickly as possible. And just once again, to keep the number simple, you move at 1 meter per second. The moving walkway moves at 1 meters per second. You can assume the moving walkways as long as you like, and you can assume the interval, the amount of time it takes for you to tie your shoes is whatever you like. So what do you think? And please respond, because I want to test the latency settings that I have on my stream right now. So let me know what your intuition says. Do you think it doesn't matter if you tie your shoes just like standing, or do you versus on the moving walkway, or do you think it'll make a difference? And if you think it makes a difference, do you think you should do it on the walkway or standing? So Jamie says on the walkway. Okay. Any other guesses? Anyone else would like to guess and think about it? Okay, it seems that Jamie has the, wait, there's another guess coming in. I think it doesn't matter, even though intuition says tie on the walkway. Okay, all right, so I'm gonna accept these two guesses. And I wanna show you that a part of the utility of the space-time diagram is just how it just like melts away this type of problem. So here's I'm just gonna, and you can think of this as just like a back of the envelope type of calculation. You can do this very quickly. So for example, let's say this is what it looks like. This is what your world line would look like if you were to not pause at all. Okay, let's say you were to not pause at all. So maybe it would look something like this. You have a slope of 1. Let's say this is, the units here are seconds. This is time in seconds. This is distance in meters. You're going 1 meter per second. You're traveling on a line. This line here has a slope of 1. Then all of a sudden, you get on the moving walkway, and let's say you keep walking. In this case, you'd be moving at 2 miles an hour, and this is where it gets a little counterintuitive. So you'd have a slope 1/2 on the space-time diagram. So, we have another guess. Pankaj Chaudhary says, it feels like it should not matter. Okay, so This is my, by the way, I do have some animations coming up, but for this puzzle, I actually wanted to illustrate that this is a quick back of the envelope kind of thing. And I wanted to improve your intuition with the space-time diagrams. So, at first you go a meter per second, you have a slope of 1, then you get on the moving walkway. Let's say the moving walkway is at this particular, position, wherever it is. And then you're on the moving walkway, and then, you get off the moving walkway, you're back to moving 1 meter per second, and then you hit the terminal. Let's say the terminal is this whatever this distance is away from you. Okay. Now you have two options. So in order to make my intuition about this problem a little bit easier, I'm going to pretend that either A, I pause to tie my shoes right before I get on the moving walkway, okay? Or B, I get on the treadmill and then right away start tying my shoes. So those are the two situations that I would like to compare. Okay, so what would the world line look like in the situation where I pause to tie my shoes right before I get on the moving walkway? Okay, so let's say I'm in that situation. So let's say the amount of time it takes to tie your shoes is, let's say this much. I'm going to draw a little, two vertical dashes. And so this is the amount of time, let's say, it takes for you to tie your shoes, okay? This is the time interval it takes to tie your shoes. So in this situation, if you decide to tie your shoes, right before you get on the walkway, you're causing yourself essentially a delay of this amount, right? Then you hop on the walkway, and everything else is the same. Okay? Once again, keep in mind we're doing just like a back of the envelope kind of thing here. Let me know if there are any questions about this. Okay, so this is the time delay you cause, and then you decided to pause and tie your shoes right before you got on the walkway. So that's what this looks like. Now let's look at the other situation where you put your foot on the walkway and then you start tying your shoes. It's also safer to do it off the walkway. That is true, but relativity cares about no such things. I'm just messing around. But, okay. If you pause on the walkway, your line would have a slope of 1, right? So your line would have a slope of 1. And then you stop at that exact instant, which is how long it takes to tie your shoes. And now your geometric intuition, just like you have this little nice right isosceles triangle over here, will tell you that you will actually be getting ahead here in this situation. So this is like an almost no numbers calculation. Hopefully this is fairly intuitive. So if you start tying your shoes right when you get on the walkway, you'll be moving at 1 mile an hour for the duration of time that it takes you to tie your shoes. So your world line will have a slope of 1 as you go. And then you're done tying the shoes, you start walking again, all of a sudden you have a slope of 2, right? And then when it ends, you start walking at a slope of 1 again, and notice you hit the terminal sooner. Okay? Interesting, right? So I just wanted you to get used to these space-time diagrams and world lines. Hopefully it all makes sense, and hopefully you can see that these are a pretty good and intuitive way to think about things. So let me know if there are any questions about this. I'll also leave you with a second version of this puzzle, which I'm curious to see your answers of. Just leave it in the comments of this video whenever you get the chance. So the second version of this puzzle is, let's say you have a little, I don't know, like an energy drink in your pocket or something, okay? And same situation, there's a moving walkway in the airport, right? And when you drink your energy drink, right, it boosts your speed by an additional It boosts your speed by an additional meter per second. Okay, so you drink down your energy drink, and then you're going really fast. And so now the question is, should you do that off the walkway or on the walkway? So that'll be the puzzle I leave to you. And this one is also very easy to analyze quickly using space-time diagrams. Okay, so if there are no questions about this, I'm going to, and hopefully the usage of space-time diagrams makes reasonable sense to you guys. It's just lines and slopes. It just graphs and lines and slopes, and hopefully all of this stuff is seeming extremely reasonable to you guys. Okay, but let me know if there are any questions about this. All right. One angle to get into the ideas of special relativity is to think about the Doppler effect. Okay, it's like a nice little avenue to get into the ideas of special relativity. It's at least it's the simplest one that I could find. And by the way, the derivation that I'm going to show you today is actually extremely close to Einstein's original derivation, which is nice. You know, it has some historical heft to it. So I want you to think about the following situation. Let's say you are out here at this particular position, okay, and you are standing still, okay? Then your space-time diagram, you know, is just going to be a vertical line over here, right? Now, let's say there's an ambulance, maybe it's traveling from this position, and it's coming towards you, okay? So there's an ambulance, it's traveling, let's say at some velocity v, and it's just coming towards you, and then it goes past you at some point, okay? Hopefully quite reasonable. Since we're thinking about the Doppler effect, let's say that this ambulance emits sound waves, okay? So, you know, we can insert numbers into the problem later, but the idea is very simple, you know? So let's say at fixed time intervals, so fixed intervals of time here, I don't know, there's like the peak of the ambulance's wave is emitted, okay? And the wave travels, let's say, at a certain speed. So you can imagine the waves coming out in this situation. And they would be leaving the ambulance in either direction, okay? Now, I did make a little, I wrote like a quick little thing in Mathematica to do this. And, you know, it's nice to use Mathematica for these types of things because it's quite fast. So let's think about the situation that we find ourselves in. So let me make sure the animation is sufficiently slow. Okay. Okay, it is pretty slow. So the purple line, that's very tiny right now. Hold on, let me make this a little bit bigger. Okay, so the purple line is the path of the, is the world line of the ambulance, okay? Let me know if you have any trouble seeing it. And it's starting from a randomly chosen position 0. So, you know, I've set things up so that you can put in whatever velocities and positions you want. I know I've asked this before, but let me know if any of you want, like this notebook. You can play around with it. You can change the velocities and analyze the Doppler effect for yourself. I do need to at some point make you know, a Davra Math GitHub page or something so I can actually share these documents. But, you know, one thing at a time. So you have the ambulance, okay, and it's moving. Its world line is the purple line, okay, and you are staying still, okay. You are staying perfectly still. Now at fixed intervals, there's a sound wave coming off of the ambulance, okay. So these yellow lines are the sound wave that comes off the ambulance, okay. Now the neat thing about sound waves and waves in general, and this is part of what led people to look into this stuff, is that the speed of propagation, I believe, is not impacted by the fact that the thing that's emitting the wave is going at a certain speed. And this is in contrast to the way that you would expect like a particle to behave, right? Like if you're standing on top of the ambulance and chucking balls off the ambulance, then the speed of those velocities from some left side seems cut out. Let me just move it over a little bit. All right, let me know if that looks good, Hitoshi. And thank you for the feedback, and thank you for showing up. So, you know, if I'm like chucking balls off of the ceiling of the ambulance, then you know, the velocity of those balls would be impacted by the velocity of the ambulance. You know, so throwing them out back behind the ambulance would be very different to throwing them forward out of the ambulance. But waves don't seem to behave that way. In fact, I'll quote the paper that I'm. There's like a good quote about this in the actual paper. A subtle but important point here. Let me zoom in here. The speed of sound does not depend on the speed of the object emitting that sound, whether the sound originally came from a moving object or a stationary one. It will propagate at 300 meters per second. This is a feature of waves in a medium, in this case, sound waves in air, which stands in contrast to the behavior of particles. An object thrown from a moving platform tends to have a different speed than the object thrown from a stationary platform. This distinction led to problems with understanding the behavior of light, which acts both like a wave and a particle, and was part of the puzzle that led to the development of special relativity. So I want to just make that point clear. This is like a very wavy thing that sound waves do. Even though the ambulance is moving, the speed of propagation of like the wave in both directions is going to be exactly the same. Okay, purple line is the world line of the ambulance. Yellow lines are the sound waves leaving the ambulance, okay? Cyan line is you standing somewhere, okay? And if I hit play, eventually one of these sound waves is going to hit you, right? And so I marked this with a red point over here, all right? And as you can see, there'll be multiple red points where the sound wave from the ambulance hits you. Of course, it's hitting you all the time, but you'll have to forgive this simplified diagram. You can think of it as a specific part of the wave hitting you. So you get that. And then at some point, the ambulance will pass you, right? At some point, the ambulance will pass you. And then like the frequency with which these waves are, or like the peaks of these waves are hitting you, these are going to be much further apart. So this is an illustration of the Doppler effect. And of course, if you've heard an ambulance passing you, it goes, so so this diagram with its world line and its waves illustrates this precise effect. Okay. Hopefully this seems extremely reasonable. So if you have an ambulance coming towards you, you can think of the sound waves kind of propagating out of the ambulance and hitting you. And then, these red dots are where the wave kind of makes contact with you. What we want to do is analyze basically what happens to the frequency of these waves, So the waves are kind of coming out of the ambulance at one frequency, but they're hitting you at a very different frequency. And hopefully this analysis with these world lines makes this abundantly clear, okay? Hopefully the analysis with the world line makes this abundantly clear, okay? Before we leave, I want to talk about what might happen if the waves leaving the ambulance bounced back off of you and came back to the ambulance. So this was the situation with, if you have a police officer using one of their radar guns to try and figure out the speed at which you're traveling. The whole way that works is, they're bam, bam, they're shooting these sound waves, or I guess, I don't know what kind of waves it is, but it'll hit your car and come back to the police officer, okay? So in this case, there's like a two-way Doppler effect, and I put this in as well. You can see this over here. Okay, let me just do my best here. Okay, let me zoom in. Let me make sure the animation runs at like a slower speed. Okay. Okay. So now you have the sound waves kind of leaving, I guess you can say the police car's radar gun. And then after hitting this stationary car or whatever, they reflect back at the same velocity going back to the police officer's radar gun. So let me know if any part of this diagram doesn't make sense. But I think it's reasonably simple. So you have, this purple line is the police person traveling in their car, shooting their radar gun at, I guess, a parked car. And then the sound waves hit the parked car and come back to the police officer, okay? So this is what that situation will look like. And these green dots over here I've marked out are where the wave kind of reflects back off of the parked car and makes contact with the police officer's radar gun again, okay? Hopefully that seems very reasonable. Okay, so this is what this diagram would basically look like. And you can see There it is. Okay. Now I want you to notice something about this. I tried to pick easy numbers in terms of these, these slopes and frequencies. So basically, the frequency essentially triples. Okay, the reflected back frequency triples. Okay, hopefully that's clear. So you can just count the dots, right? So this segment over here represents like you can think of it as the emission of like one wavelength or whatever. And you notice this one segment gets divvied up into 3 segments over here if you count the dots. Let me know if that makes sense. And so when the police car is driving towards the person, it seems like, at least with the numbers that I've chosen specifically, there's a tripling of the frequency. Hopefully that makes sense, and you can just figure that out by counting the dots. So, this one segment gets divided up into 3 segments, okay? Symmetrically, when the police officer passes in their car away from the parked car, notice the frequency triples. So you see this one green dot over here, right, has 3 of the original segments up here inside it. So let me zoom into that part of the diagram so it's clear. So see, there's a green dot here and a green dot here, and there are 3 of the original segments over here between these 2 green dots over here. So it seems like the frequency is cut down by 1/3, okay? And it's on one side when things are traveling closer together, and it seems like the frequency is tripling on the other side, okay? Hopefully that makes reasonable sense. And let me know if there are any questions about this. So just remember that for now. So it's 1/3 on this side and it triples on the other side, okay? Now here's what I'm going to do. I'm going to flip the situation that we find ourselves in, okay? So this is going to be the more realistic situation where the police officer is holding still in their car and it is the car that's traveling, okay? So the police officer in this next situation is holding still and it is the car that is traveling, okay? So now the sound waves will be emitted from the stationary object as opposed to the moving object, and the sound waves will bounce off the moving object. Ken says, I think you meant it the other way around, triples on approach and divides by 3 when receding. Yeah, that's what I meant. I'm sorry if I said it the wrong way. So yes, good observation, Ken. Sorry about that. So it makes sense. Okay, so this is what we have over here. Okay, now let me flip the let me like flip the code. So I need to just like swap the lines in the code. So it'll be 0, 5, 1, 0, 0. And yeah, do let me know if you want to like play around with this. I can put it up somewhere for people to mess around with if anyone cares. Okay, let's go back here. Do this. Zoom in over here, and all right, it's going a little fast. Let me just make it slightly slower. Okay, so now you can see the police officer's car is still cyan, and you can see the sound waves coming off of the stationary object. Let me know if you have any trouble seeing this, okay? So it goes like that, okay? And then it bounces off the moving car, okay? It comes back, and it'll make contact with the police officer's car, okay? Is the tripling independent of the speed of sound? No. I chose numbers. So Jamie asked the question if it would always be tripled, and the answer is absolutely not. I just chose numbers where you could like count the dots in the picture, so that the illustration would be clear. Okay, hopefully that answers your question, Jamie. So you have this, okay? And, okay, so again, the waves bounce back and hit the police officer's stationary car, okay? And once again, these are well-chosen numbers. I swapped the position and the speed of the police officer's car with the person who's sitting in the stationary car, okay? But you notice the effect on the frequencies is the same when you swap, Okay, the 2. So you can check in this picture as well. So the green dots represent the bouncing back off of the moving car back to the police officer's car. Okay, and you can check here that, again, this one segment gets divided into 3 segments. Okay, so the bounced back frequency is tripled. Okay, and then when the cars pass each other, it slows down, so it becomes a third. Okay, so this two-way Doppler effect is in fact symmetric. Okay, that's the point I wanted to illustrate with these diagrams. Okay, and you can check this with arbitrary numbers as well. So if you have a stationary object and an object moving, okay, then essentially the stationary object will perceive a higher frequency, than what's coming out of the object that's moving. Okay, and you can pretend that the sound wave is then reflected back onto the original object, and so that will push the frequency higher still. And you can think about, okay, what is the factor of increase in frequency when it leaves and it comes back? Okay, and that factor of increase when 2 objects are moving closer to each other actually is the same if you swap the object that the waves are coming out of. Okay, which is kind of interesting. So this two-way Doppler effect is symmetric. Okay, as maybe you expected it would be. This two-way Doppler effect is symmetric. So let me know if there are any questions about that. So this two-way Doppler effect being symmetric is interesting, okay? But what about the one-way Doppler effect? What if I'm just interested in what happens to the frequency when you like leaving the moving object? What happens to the frequency perceived by the stationary object, and what happens to the frequency when it's coming out of the stationary object and then it hits the moving object? What is the effect on the frequency over here? So I'm just going to erase all of my reflected lines from the diagram. So I think it's just need to comment out these lines of code and hit enter. Okay, in this situation, okay, now the waves are coming out of the stationary object. Okay, and we would like to see the time interval between the waves, quote unquote, as it hits the moving object. And so you can just type in that it's 2/3 apparently, just the numbers I chose. It's going to be 2/3, okay? And this 2/3 is coming from the numbers I chose from the slopes of this diagram. It's not like some universal constant or anything like that, okay? But as you can see, whatever the original frequency was, the new one is 2/3 of the original, just based on the numbers that I chose. And this is the situation when the waves are being emitted from the stationary object. Okay, there's a dilation effect of 2/3. Okay, but what if we swap and now the waves are being emitted from the moving object? Okay, but what if we swap now and the waves are being emitted from the moving object? Well, let me just swap the lines real quick, the emitter and the non-emitter. Okay, in this case, it's a half. Interesting. So the two-way Doppler effect wound up being symmetric, and the one-way Doppler effect is not symmetric. So it seems to depend, like the amount of dilation here that's experienced seems to depend on if the waves are coming from the moving object or the stationary object. Which is very interesting. Okay, before I proceed further, we need to actually do some math now. Enough pretty pictures. We actually need to figure out exactly the amount of dilation, or like the exact amount that the frequency is changing in this situation. Okay, so I'm just going to draw like some basic lines with slopes, and we're just going to figure out what is going on with the stationary object and the waves. Okay. So just some constants over here. I'm going to say v is going to be the this is the speed of the moving object, okay? And I'm going to say that, okay, let me do that real quick. So also, I have to say, are they moving towards or away from each other? For now, let's just figure out what goes on when they move towards each other. Okay, the effect when they're moving away from each other is going to be 1 over when they're moving towards each other. So hopefully that makes sense, Mohammed. But so you have v. Okay, so v is the velocity. Well, we're working in one dimension, so I guess it's just about direction. But you can think of v as just the speed of the moving object, and the stationary object is, of course, stationary in this situation. Now, I'm about to do some math in front of people, so for my comfort, I'm going to swap the x and y axis of the space-time diagram, just because I believe I'm going to be far less error-prone. In this way. I'm sure all of you physicists out there are not going to be happy with me, but you do something the same way for 10 years, it kind of sticks. So I'm going to draw my diagrams like this. So this is going to be my time. I'm so sorry. And this is going to be my position. Okay. So now my stationary object is just going to be represented by this flat line. In this situation, okay? Let's say the stationary object is at position P, okay? Hopefully that makes sense. And my moving object is going to be like so. And this, if it has a velocity of v, then the equation of this line is just x equals vt. Hopefully I'm not blowing anyone's mind over here. But this is going to be the equation of the moving object. Okay. Now, off of this moving object, there are going to be essentially some waves that are coming off. Okay. And so, let's say the first one comes off right at the start, just to make life easier. Okay. And the second one, let's say, comes off over here. All right. So here's what we're going to do. So we are going to, and yes, so hopefully this clarifies your question, Mohammed. We're doing this derivation when they are coming towards one another. Okay. So let's say this is W. This is the time gap between the emissions of these waves. So you can think of it as the time gap between when two peaks of the waves are emitted. Okay, so we're going to think of this as W. So what would the coordinates of this point be? The coordinates of this point are going to just be W, comma, VW. I just plugged it into the equation of the line. Okay. Hopefully that seems reasonable. And so what is the equation of this line going to be? Because we're eventually going to be working with light, I'm gonna say that the sound waves propagate at speed c, and then when we're done, you'll just start thinking of c as the speed of light. But the sound waves, let's say, propagate or whatever waves. This could be like radiation or something. I don't know. But if whatever wave this is has a speed of c, then the equation of this line is going to be x equals ct. Okay, but that seems reasonable. In which case, the coordinates for this point up here, and pause me if any of this doesn't make sense. I mean, what are the coordinates of this point going to be? Well, I have to just, so the time at least will be p over c. The full coordinates of this point are p over c comma p, but I'm just going to write the time coordinate just because I'm running out of room over here. So once again, I'm just doing basic line intersection arithmetic. So even if you're not following along, this should not be too hard for you to check. Okay. What is the equation of this line going to be? Right? What is the equation of this line going to be? Well, we can use point slope form. You remember that from a long time ago. The slope of this line is still c, right? So the equation of this line is going to be x equals c times t minus w plus vw, because the line has a slope of c and goes through the point w comma vw. Now, hopefully that makes sense. Okay, so then what is the coordinate of this point going to be up here? And remember, I'm only interested in the time coordinate. The position coordinate is definitely just going to be p. Okay, so if I solve p equals c times t minus w plus vw, okay, what's going to happen here? I'm solving for t, right? So this is going to be P minus VW, right? P over C, VW over C plus W is going to equal T. Okay, and please correct me if I messed up at all. Okay, so this time is P over C, and the time for this point is, let's see, P over C plus W minus VW over C. Reasonable? I hope so. So the gap between emissions, or however you want to think about it, whatever you want to call it, started out as W, and then the gap here is whatever the gap between these two times are, right? So the gap up here is going to be the difference between these two, which is just W 1 minus V over C. Okay, which you can rewrite as is tradition as W times C minus V over C. So you start out with W. Okay, the stationary object will will get a time between difference of with a factor of C minus V over C. Okay, so just keep that number in mind. So it's going to be C minus V over C is going to be the shrinkage coming from the moving object to the stationary object. Okay, and this is just line arithmetic, so hopefully it makes sense. Now let's do it the other way. Let's pretend the waves are coming out of the stationary object and hitting the moving object. Okay, so let's pretend the waves now are coming out of the stationary object and hitting the moving object. So remember this dilation factor over here. It's C minus V over C. And thank you, Mohammed. Okay, so C minus V over C. We'll throw that up here somewhere just so that we can remember it. All right, now let's do our simple line math. In the situation where the waves are now coming out of the stationary object and hitting the moving object. Okay. All right, so this is my stationary object, again at position P, and this is my moving object. This again has equation x equals v t. Pretty reasonable. But now our sound waves are coming off of the stationary object, so they'll be pointing kind of downward, like so. All right, and then there'll be another one a little bit later coming downward like this. Okay, so again, let's assume that W is the distance, the time difference between these two quote-unquote emissions. So, right, so now we just need to do the same thing again. We need to figure out the time coordinates of these 2 points. Again, this is our position axis, because I draw my space-time diagrams backwards so I don't make a mistake. We'll see what happens. So what is this point going to be? Well, it's the intersection of these two lines. I mean, what's the equation of this line over here? Well, this line has a slope of negative c, right? And it has a y. It has an intercept over here of p. So it's just going to be x equals negative ct plus p. Slope intercept. Hopefully that makes sense. And so to figure out what the time coordinate for this point is, we just need to figure out where these two intersect each other. So in the corner here, I'm just going to solve vt equals negative ct plus p. And it just so happens that, what is t equal to? I guess t is going to equal p over v plus c. Reasonable? So the time for this one is going to be p over v plus c. That's I only wrote down the time coordinate, not the position coordinate, because the time coordinate is the one that I'm interested in. But the time coordinate for this point is going to be p over v plus c. Okay? What about this one over here? Well, for this one, we need to figure out the equation of this line. In order to do that, I mean, I guess we can use point slope again. So what would this point be? Well, this point has an x coordinate of p and a t coordinate of w, I guess, right? Because it's w off this way and p up this way. So this is just w comma p, this point up here. And then what is the equation of this line going to be? Well, again, this line has a slope of negative c. So this is going to be x equals negative c t minus w plus p. Again, slope-intercept form. Okay, so x equals negative c t minus w plus p. So in order to figure out where these two intersect, I just need to set this equal to vt. So let me do that in this corner over here. So you get vt is equal to negative c, let me write it like this, negative ct plus cw plus p, which would mean that t is in fact cw over c plus v, and then plus p over c plus v. Okay, so the time coordinates for this point are p over v plus c, and then plus cw over c plus v. Okay, so the time difference between these 2 points is cw over c plus v. So you start out with a time difference of w, and then it becomes cw over c plus v, which means that the time difference between these new ones is c over c times v times the original difference. Okay, so this illustrates the asymmetry here in the one-way Doppler effect. You have the waves coming out of the moving object. You get a factor of c minus v over c. But you have them coming out of the stationary object, you get this factor, c over c plus v. Okay. How might you explain this? By the way, let me know if there are any questions about this. How might you just explain this simply? Well, you know, there's a classic, a very simple explanation for the difference between these two. So the reason the effect is different is because the medium of propagation is moving from one person's perspective, but is not moving from the other person's perspective. Okay? So from the stationary person's perspective, the medium through which the wave is traveling is not moving. But from the moving person's perspective, it is moving. Okay? So in fact, if you think about it that way, it makes sense that the one-way Doppler effect would be different. Okay? You can explain that. You can explain this lack of symmetry. Okay? And yes, John, you're correct. The factors are very close if v is a lot smaller than c. But you can explain the difference between these two using a medium. But let's turn this reasoning around. Okay? Let's turn that reasoning around. If the best explanation we have for the medium, I'm talking about like air, you know, like sound traveling through the air or something, okay? So the medium through which the wave travels is moving from one person's perspective, but not from the other person's perspective. Hope that answers your question, Mohammed. Okay, so in fact, let me state it another way. If your wave needs to travel through a medium, you would expect to see an asymmetry in the one-way Doppler effect, right? Makes sense. So you would always expect to see this kind of asymmetry in a circumstance where the wave, or whatever kind of wave it is propagating through a medium. And I believe, I'm not an expert on this topic, this type of thinking led people to hypothesize that light also, you know, needed a medium to go through, and the medium was called ether. Okay? This is the medium that people thought that light traveled through, or at least people theorized thinking this way a long time ago. So the idea was light travels through this medium called the ether, and it made sense, and people thought about it this way. But then again, if light travels through a medium called this ether, or needs this medium to go through, then you would expect to see the same asymmetry when you look at light, right? You would expect to see the same frequency difference depending on whether or not the person emitting the light is the one moving and the person capturing the light is holding still, versus if the person holding still is emitting the light versus the person and the person traveling is the one capturing the light. So Ken Haley says, so the symmetry would be reversed if the speed depends on the speed of the source. Yeah. So one of these tells you what happens to the effect on the frequency if so v is the speed of the source, c is the speed that the wave propagates through, and you have this asymmetry over here. But the issue is, when people started experimenting with light, they found that light actually does not experience a one-way Doppler effect, okay? Which is extremely confusing, okay? So light, it doesn't really matter if the person traveling is the one emitting the light and the person holding still is the one capturing the light, versus the person holding still is the one emitting the light and the person moving is capturing the light, okay? Which is really weird, which throws this whole ether idea out the window. You need a new way to think about precisely what is going on here, okay? So to make a very long story short, it was Lorentz who came up with a potential idea for a solution to this problem, okay? And his idea was very simple. The idea is that as an object travels more quickly, the object experiences time dilation, okay? So everything for an object traveling quickly, everything gets slowed down by some factor, this time dilation factor, lambda, okay? All right, so this is the idea over here. So if this theory is true, and by the way, this has already been experimentally verified, there'd be a lot of kind of mathematical ways you can resolve this paradox of light not experiencing an asymmetric one-way Doppler effect. There are a lot of mathematical ways to do it, but this one actually wound up being the one that experimentally held true. And the idea is that a time is essentially slowed down for an object that's moving with velocity. Okay, so essentially you get the following equation. So because time is slowed down, you get the following idea. You get lambda times c minus v over c, okay, should equal 1 over lambda c, 1 over 2, 1 over 2, 1 over lambda c over c plus v. Okay, so this is fundamentally how Lorentz managed to resolve the idea that you don't experience an asymmetric Doppler effect when you start examining light. You need to slow everything in the moving object by a factor of lambda, essentially, where lambda is some number, I suppose, that's less than 1. Okay, and from here, actually, you can solve for what lambda needs to be. And so, by the way, lambda is simply chosen in a way that will make the one-way Doppler effect asymmetry vanish. Okay, that's the whole point of lambda. So you want to choose a time dilation that will precisely kind of cancel out these two numbers not being equal to one another. Okay. So hopefully that makes sense. And so from here, you immediately see that lambda must equal, I guess it would be, well, I guess lambda squared would equal c squared over c minus v times c plus v, which is going to give you, I guess, c squared minus v squared. Okay, so now we can solve for our Lorentz factor over here. So this time dilation factor is going to be precisely, you can pull a c squared out of the denominator and cancel it with the 1 in the numerator and write it like this: 1 minus v squared over c squared equals lambda squared. And in essence, you can solve for lambda now, and it's going to be the square root of 1 over 1 minus v squared over c squared. So this, you need this kind of time dilation factor in order to get this one-way Doppler asymmetry to vanish. Okay, so let's think about this. what would happen? So if we insert this lambda into our equation, so let me rewrite things. We've already solved for lambda. Lambda is going to equal, what was it? It was like 1 over the square root of 1 minus v squared over c squared. Okay, so now if you go back to the equation we used to derive lambda, it was lambda times, what was it? Lambda times c plus v over c is equal to 1 over lambda c over c minus v. I may have kind of cross-multiplied. So it was this, but I potentially cross-multiplied it. But whatever. It's the same equation, fundamentally. Okay? And notice when you insert this factor of lambda into the mix, if you throw in a 1 over square root v squared over c squared, c plus v over c equals 1 over lambda. So in this case, this would just be the square root of 1 minus v squared over c squared times c over c minus v. At this point, both sides of this equation should be equal because we constructed our constant lambda precisely so that this would be the case. So let me just solve for one side of the equation. The other side should be exactly the same. So this is, let's see, so we can, this is a c. So if I put this in here, like if I take this c, turn it into a c squared, and put it inside the square root, I would get c squared minus v squared divided by c minus v, right? But then c minus v, so you can rewrite this as the square root of c minus v times c plus v. And you can rewrite the denominator as just the square root of c minus v squared, square root of c minus v, quantity squared. So c minus v, c minus v. This lets you cancel out the c minus v's. And now, without this asymmetry in the one-way Doppler effect, you get that the effective dilation in both cases, right? In both cases, where the moving one is emitting the light and the stationary one is recording it, versus where the stationary one is emitting the light and the moving one is recording it. In both cases, the factor that the frequency is affected by is going to be precisely the square root of c plus v over c minus v. So putting all this together, square root of c plus v over c minus v, this is now taking into account this Lorentz term lambda. Taking that into account, this number is describing the ratio that's going to happen when you experience a one-way Doppler effect due to light. And this is going to be symmetric in both cases. So let me know if that makes sense. Let me know if that makes reasonable sense. And if not, I'm just going to move on. The next thing I'm going to do is just derive equals mc squared. So I hope you're excited about this. Okay. So the next thing I need, so this is essentially if you have two things that are getting closer to one another, and it doesn't matter which one is emitting the light anymore, right? Because we've kind of canceled out the effect of the one-way Doppler effect. But if this one is moving towards this one, let's say, and emitting light, this is going to be the factor that'll tell you how this one is experiencing the frequency, right? And it doesn't matter either way. If things are moving away from each other, by the way, it would just be the reciprocal of this. It would be c minus v over c plus v. This is the factor that you would need to figure out the frequency in the situation where you have two things moving away from each other. One of them is emitting light. Okay. All right. Now, what you can do is, and so first of all, let me write down a few equations. So from quantum mechanics, we have this equation that says the energy of, you can compute the energy as being proportional to the frequency of the wave that you're working with. And the constant of proportionality in this case is called Planck's constant. By the way, we won't need Planck's constant. All the Planck's constants in our computation are going to cancel each other out. You can pretend this is whatever constant as you like, but you do need this idea that the energy is proportional to frequency. And Jim, yes, this does in fact solve for redshift, to answer Jamie's question. So the three facts that I need, so I have this fact, that if two objects are coming towards each other, this factor will tell me the effect on the frequency. And if they're moving away from each other, the reciprocal of it will tell me the effect on the frequency. The second fact I need is that the energy is proportional to the frequency of, say, a photon or something like that. Okay? So hopefully all of that makes sense. So in order to figure out the mass energy equation, okay, we have to say that, okay, let's say you have an object with a certain mass, okay? And let's say it disintegrates into two particles, okay? So two photons. And let's say one is going this way and the other is going the other way. I know for a fact this is not the correct notation or anything like that, but, let's just continue with this. So you have some mass and it disintegrates into, let's say, two photons. One goes one way, one goes the other way. And you, the observer, are maybe looking at it. Okay? Now, this type of interaction is, of course, an oversimplification. So I'm just going to read the comment to you from the original paper. In practice, disintegrations are more complicated than this. For instance, an elementary particle might decay into two particles plus a photon. But to simplify the discussion, we will just consider the disintegration of mass into two photons. This situation can occur when the mass consists of a particle together with an antiparticle. For example, an electron-positron pair. So, is energy being proportional to frequency a classical physics assumption? Did Einstein use it? I believe Einstein used something close to it. You can read the paper if you would like more details, but I do believe this is something coming from quantum mechanics. We're trying to give like the simplest derivation possible. So I don't believe this is from classical physics, but maybe someone knows more than I do. I don't believe Einstein used something like this, but regardless, I'm sorry, he did, I'm not sure if he used exactly this, but I think he used something like it. Remember, this is supposed to just be close to Einstein's derivation, and the attempt is to be as simple as we can possibly make things. Okay, so hopefully that's clear. So energy, all we need in this case is energy being proportional to frequency. And you're going to pretend some mass is disintegrating into two photons, one going this way, one going the other way, as apparently can happen when you have, I guess, an electron and a positron interacting with each other. Okay. In this situation, notice if you, the observer, are like, I don't know, standing right where the mass is, right? There's going to be a Doppler effect here, right? So there's two ways to think about the energy in this circumstance, right? So you have the energy is equal to Planck's constant times the frequency. In this case, you have two particles coming out of a single mass. So in this case, the energy is going to be 2hf, right? One for each particle, okay? I'm sorry, one for each photon coming off of this interaction. Okay, 2hf, one for each photon. Hopefully, so far so good. Okay. However, I'm going to pretend that I, the observer, am just driving by at some velocity v. So I'm observing this interaction at some velocity v going past this. Okay, you can set v to be whatever you want it to be, but let's pretend that I am, some observer, velocity v. Well, notice I'm going towards this photon, but I'm going away from the other photon. Okay? So if I'm measuring the energy using the same equation, I would get something a little bit different. I would get h times the square root of c plus v over c minus v times f for the one I'm moving towards, and plus, all right, nice to see you, Ken. H, for the one that I'm moving away from, it's going to be H times whatever the factor is, C minus V over C plus V times F, okay, times the frequency. So if I, the observer, am moving some velocity V away from this experiment, then I'm going to be moving towards one of the photons away from the other photon. So if I measure the energy here, it's going to be H square root of C plus V over C minus V F plus H square root of C minus V over C plus V times F. Hopefully that makes sense based on our discussion of the Doppler effect. Okay? But you might object and say these two measured energies are not the same, right? They're simply not the same. On the one hand, I have 2HF, and on the other hand, I have this slightly messier equation. Okay? The way to square this circle is the difference between these two energies should be, kinetic energy, right? The motion, V. So essentially what you have here is 1/2 mv squared, which is the kinetic energy, is equal to the difference between these two. So this is going to be H. I'm actually going to need a lot of room for this. So I'm just going to make a lot of room. So now you have 1/2 mv squared is equal to H times the square root C plus V over C minus V times F plus H square root of C minus V over C plus V times F minus 2HF. Okay? The idea being the difference between these two energies is explained by the kinetic energy. Okay? That happens because your observer is just like moving past the system. Okay? And I claim messing around with this will give you E equals mc squared. Okay? Exciting. All right. So let's mess around with it. So now I have this is equal to, I can take an HF common in this equation. Okay? So I have HF times square root C plus V over C minus V, right? Plus square root C minus V over C plus V minus 2. So far, so good? All right. Next thing I'm going to do is I'm going to take a common denominator here. Okay, I'm just going to take a common denominator here. The common denominator here is going to be the square root of C minus V times the square root of C plus V, which should be the square root of C squared minus V squared. Okay, so this is going to be the square root of C squared minus V squared. Okay. I've taken the common denominator now, so this is going to be minus 2 times the square root of C squared minus V squared. Okay. And let's see, I'm multiplying C plus V with C plus V and taking the square root. So that's just going to give me C plus V. And then I'm multiplying C minus V with C minus V, and then I'm taking the square root. So that should just give me C minus V. So this is plus C minus V. All of this times HF. Okay? So now this will give me HF. The V's cancel. This is 2C minus 2, so I can take a 2 out common, right? This is going to be C minus 2 square root C squared minus V squared over the square root of C squared minus V squared. Hopefully, everything so far is reasonable. I'm going to move this to the top. Move this up. Uh-oh. Hold on. All right, I'll do this. Done. Deselect. Erase. 1/2 v squared is equal to this. No need second 2. Oh, yeah, you're right. Thank you so much. Thank you so much, Hitoshi. I do not need the second 2. You're absolutely right. OK, thank you. So now I have this, and it's c squared minus v squared. OK, now what I'm going to do is I'm going to pull a c out of everything. So I have 2hf c minus c square root 1 minus v squared over c squared over c times 1 minus v squared over c squared. All right, now I can cancel the c's. I have 2hf. By the way, 2hf was the energy, right? If you recall, the energy of the 2 photons going in both directions. So I'm just going to replace this 2hf with an e. OK, all the c's cancel. And now I have 1 minus the square root of 1 minus v squared over c squared divided by the square root of 1 minus v squared over c squared. OK, now I'm going to move this up in an attempt to not run out of room. Oh, shoot, I should have erased above it first. So now I have this done. Deselect. All right. Now what I'm going to do is I'm going to multiply the numerator and the denominator by 1 plus the square root of 1 minus v squared minus c squared. I'm basically doing the a squared minus b squared equals a minus b times a plus b trick over here. So now I have e equals, the denominator will be the square root of 1 minus v squared over c squared times 1 plus the square root of 1 minus v squared over c squared. Because remember, this thing here is what I'm multiplying the numerator and the denominator with. But when I multiply the numerator with this, this will be a squared minus b squared. So that's 1 minus 1. And then just over here, it's just going to become v squared over c squared. OK? But remember, the velocity that you're driving by with, you can just assume it's much smaller than c, right? You can just assume that v is much less than c, right? In which case, the limit of this expression is just going to be, well, the limit of the denominator is just going to be 2. This will limit to 1. This will limit to 1. This will limit to 1. So that's a 1 times 1 plus 1, which is 2. So you have that this is approximately e times v squared over c squared divided by 2. And so now you have the equation 1/2 mv squared equals e over 2 v squared over c squared. The v squareds cancel. The 2's cancel. You just take the c squared on the other side, and there you have it. E equals mc squared. Derived from scratch from the from getting rid of the asymmetry in the Doppler effect using time dilation, and by just viewing the disintegration of a mass into 2 photons from basically 2 different perspectives, you can use it to derive E equals mc squared. Okay, I had a lot of fun with that one. I hope you guys did too. Let me know if there are any parting questions. Also, let me know if there are any issues with the stream quality, because I set it on low latency this time, so I hope it made the stream run more smoothly. But in any case, that's E equals mc squared. We skipped a million different issues doing this. And also, not being like a trained physicist, some of the terminology I may have used is probably not going to be like completely accurate. And of course, thank you, Brian, and thank you to everyone that showed up. I really, really appreciate it. I still don't know what the equation means. So Yeah, so many things to think here. I guess I'll leave you with Einstein talking about E equals mc squared. Hold on. This is a classic video. Let me know if you can hear the audio on my desktop. I need to make this like way low.
From the special theory of relativity, that mass and energy are but different manifestations of the same thing. A somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is thought equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Kokra and Walton in 1932 experimentally.
All right, there it is. So that was Einstein himself talking about it. Hopefully that answers your question. And like I said, it's been, or like he said, it's been verified by experimentation repeatedly. All right, that's more than enough out of me. So I hope you guys enjoyed that. I'll be streaming again on Wednesday at 1 p.m. I appreciate all your feedback, even criticism. So let me know if there's any way I could improve these streams. I'm doing my best out here, but I would like to know if you have any feedback that you think might help. And thank you again all for showing up. And I think that's all I need to say. All right, peace.